Now that we learned the different bracketing methods in solving for the roots of nonlinear equations, we move to the simpler approaches known as open methods. They are faster and more efficient in looking for the values of x. Learn about open methods in numerical solutions to CE problems. Let's review a bit about how to determine roots of nonlinear equations. There are the so-called non-numerical approaches where one only needs to plug in the equation in a graphical calculator in order for us to find the roots of a given nonlinear equation. So in graphing, in order for us to make an accurate answer, a graphical calculator is required. The other approach is just plugging in random guesses and using different intervals in locating f of x as 0 in the incremental search method. So again, this would be initial guesses and random intervals. As discussed previously, the bracketing methods limit or brackets the limits for the desired root. There are lower and upper limits. In the case of the bisection method, the succeeding value of x would be taken from a mid-value. Say that would be c, and lower and upper limits would be a and b. Take the average to have the mid-value, and that would be for the succeeding values of x in the other iterations. Note that in bisection method, this would be regardless of the inclination of the slope. How about in regular falsi method? Although we are going to have lower and upper limits, the formula for the succeeding value of x would be taken from linear interpolation, whereby this would mean that we are going to somehow work with the inclination of the curve. The formula being c is equal to a times the function of b less b times the function of a all over the function of b less the function of a. NewtonRaphson is an open method which modifies further the idea of regular falsi. In this approach, the tangent line of a point is followed. Say that we are going to consider this point, taking its x distance. Let's say that this would be x1. Y distance is taken as the function of x1. In order for us to work with NewtonRaphson method, it says that we would have to take not your linear interpolation, but your tangent line. If that would be a straight line, you'd notice that the tangent line would somehow intersect this point of your x-axis, which we are going to have as your second value of x. F of x would then be the projection of x sub 2 going to the curve. With our tangent line, we can work with like your tangent of theta. So let's say that we do have this as our tangent line. If this is our x sub 1 or f of x sub 1, and this length is taken as your x sub 1. Try to get tangent of theta. That would be taken as tangent of theta is equal to f of x sub 1 all over x sub 1. As we said, tangent of theta is taken as the opposite all over adjacent. Also note that in calculus, when we would take tangent of theta, which is known as the slope, we can have this taken as the derivative, which is denoted by f prime. Thus, in the formula, the slope is taken as f prime of x. How do we go about with the procedure of Newton-Raphson method? Say, for this example, that we are required to determine the fourth iteration of x for the function x cubed less 7x squared plus 8x minus 3 if our initial x or x naught is given as 5. The first thing to do would be for us to find f prime of x. X cubed would be taken as 3x squared minus 7. X squared would be 2x plus 8. X is taken as 1. Recall that the derivative of a constant would be c or disregarded. Now simplifying, we have 3x squared minus 14x plus 8 for our f prime of x. Now that we have our formulas, we can move ahead with our computation. It says that x naught is given as 5. If we plug in our value into the formula, that's function of 5 is equal to 5 cubed minus 7 times 5 squared plus 8 times 5 minus 3, or f of x would be given as negative 13. Plugging the same value of x of 5 to our f prime, we would also have positive 13. Next is for us to find x sub 1. X sub 1 will be using our formula. X sub 1 is equal to x naught less the function of x naught all over the derivative of the function of x naught. By computation, you would have your value of x sub 1 as 6. Plugging this value to both our functions, we would arrive at positive 9 and positive 32. Move on to our next iteration, as we are supposed to look for the fourth x value. With our formula, we would have our new value for x sub 2 as 5.71875, where plugging this value, we would have f of x as 0.84787, and f prime of x would be given as 26.0498. For our third iteration, we are going to have the same procedure, So plug into our formula of x. That would yield 5.686202, and f of x would be 0.010725, and f prime of x is taken as 25.39185. Now for the last iteration. X of 4 would be taken as 5.68578, whereby f of x is given as 1.79, and this is times 10 raised to negative 6. F prime of x is still 25.38335. So we know that our answer for x from the fourth iteration is given as 5.68578. Just in case we are going to work on our iteration, take note that what you're going to check would be f of x, whereby it's supposed to be near or close to 0. Let's check the next example. Determine the root for the function of x given x cosine x minus x squared if x naught is given as 1. In order for us to proceed, let's look for f prime of x. X cosine of x would have the formula u dv plus v du. Thus, we can take x, derivative of cosine x would be sine x, and that's negative, plus cosine of x, derivative of x would be 1. If we simplify, then we can have cosine of x minus x sine of x. Now to complete our function, f prime of x is then taken as cosine of x minus x sine of x minus 2x. Now we are ready to plug our values for the functions. If x is equal to 1, the function of x will be computed as negative 0.4597, whereby the function of prime of x using our newly found formula would be taken as negative 2.30117. We continue to the first iteration by plugging 1 fx and f prime of x into our formula. Then we arrive at 0.800233. And using this value in f of x, we come up with 0.044947. Doing the same for the function prime of x, we get negative 1.47811. And then again, we are going to plug our values to look for x sub 2. And we arrive at 0.830641. Using this value for the functions, we get negative 0.01293 and negative 1.6002. Since we are not required to limit our iteration, then we would have to look for that time where our values of x would be very close to each other. So continue into our third iteration. Plugging our values into the formula, then we have 0.822563 f of x turning as 0.003072 and f prime of x as negative 1.56763. With these values, we can again proceed to our formula in order for us to have the fourth iteration of x as 0.824523. And using this value into the functions, we get negative 0.00077 and negative 1.57552. Notice that what we have would already be until the second decimal place of 0.82. So moving on to our fifth iteration. Again, plug the values into the equation and we get 0.824036. F of x turns as 0.000189 and f prime of x would be negative 1.57356. So from our fifth iteration, you can notice that we already have until the third decimal point. So let's continue on to the sixth iteration. By plugging the values, we get 0.824156. F of x turns out as negative 0.4047 and f prime of x would be 1.57405. Since we already have a very small value for our f of x, we can already conclude that the root for the equation is 0.824156. Let's take a look at the secant method. If you are familiar with the second formula, this is taken from the NewtonRaphsons. And the formula on the left would be for secant method. Compare the two formulas. X sub 1 would still be x sub 1. This would be from the preceding values of x sub a, or x naught. There would be a function of xa, or x naught, preceded by your minus sign. Going back to NewtonRaphson, you can see that f prime of x naught would be basically taken as this whole equation. This whole equation is just working with the two-point system. In taking the slope of a line. That is, y2 less y1 is equal to m times x2 minus x1. Remember that our values for y's are taken as the functions. X would still be our x sub a and x sub b. Let's have it in detail. If this is taken as x sub a with the function of x sub a, and that is denoted as the x-intercept or the x-coordinate, and the vertical height would be given as the function of x of a. Take the other point. This would be x sub b with the function of x sub b, that is x sub b and its height, the function of x sub b. The connecting line would be what we call our secant line. This is similar with our tangent line, although secant lines would need 2 points. So take our slope, which you already know as rise all over run. The rise for this case would be taken as f of x sub a minus f of x sub b. The run would turn out as x sub a minus x sub b. And this formula is placed as the slope into the denominator, whereby we arrive at our formula for secant method. Determine the root of the function of x with the cosine of x plus 2 sine of x plus x squared that has one root within the interval 0 and negative 0.1. So take the upper limit as x sub a and the lower limit as x sub b. By using our functions with this formula below, then we can get our value for f of x sub a as 1 and that of x sub b taken as 0.805337332. How do we proceed? Next, our x sub b will be our new x sub a. So that would be negative 0.1. X sub b would be computed from the formula. And we get negative 0.51371. With the known values, then we can reach for f of x sub a as 0.805337332, which is just taken from this value, as we still have the same x value of negative 0.1. F of x sub b is then computed as 0.152002794. Repeat the process. So your new x sub a would then be taken as negative 0.51371, coming from this value. Of course, its function would be coming from our f of x sub b earlier, which is 0.152002794. Now we compute for x sub b. That would take us negative 0.60996 with its corresponding value of f of x sub b, which is 0.046051316. Continue our iteration, sliding our values for your x sub b's and also its function. Then compute our new x sub b. For the third iteration, we would have negative 0.6518, and its function would be 0.0066022258. The fourth iteration would still have the same process. Slide our values for x sub b and its function, and compute for our new x sub b. This time we have negative 0.6588, and its function would turn out as 000040908. Continue the process. Slide our x sub b and its function, and compute for our values of the new x sub b, and also its function, If we move further, then we get and the same thing for the function, and compute for x sub b. And also its function. Although we do have a very minute value for the decimal, let's check if we can find for the same value of x sub b. So let's take our next iteration. Slide the values, also for the function, and solve for our new x sub b. This time it would turn out as the same value as what we have previously. So we can say this time that the root of x would be given as negative 0.65927.